So, hello everyone, welcome to the first episode of Aerocast. Today we have with us Nishant Mittal from Electrical Department. Nishant is working as an avionics engineer in avionics and control subsystem of IIT Bombay's rocket team. He is also a part of hardware and mobility subsystem of the Mars rover team. So he will be delivering a talk on trust vectoring and enriching our knowledge. So over to you, Nishant.
Thank you, Isha, for that introduction. So, without further ado, let's begin. Some ground rules before we start off. I know a lot of you here are to learn about TVC with respect to aircrafts and want to do projects with respect to them. But I'll mostly be focusing on TVC with respect to rockets and how they work in rocket systems because it's easier to explain and it's more intuitive understanding. Will I'm always open for doubts, and we can look at how the concepts can be translated to aircrafts. But it's fairly straightforward once you get the basic idea. Secondly, please feel free to unmute and interrupt at any time for any questions, queries, doubts, discussions, clarifications, or corrections. Though I hope there are none of the last. I cannot see the chat box, so you will have to speak up or ask one of the moderators to speak up. So please do that if you have any of the above. And last but not least, hope you have fun and learn something. So let's start off. First off, let's talk a bit about control. What exactly is control? Why do we need control? And what's it all about? So, as the word suggests, control is a way to control your vehicle, to get it to do what you want it to do. Depending on your requirements, depending on your flight plan, depending on what you want the vehicle to do, you're going to have some sort of trajectory for the vehicle, some sort of path, some sort of mission criteria you want it to fulfill. For that, you want the vehicle to go on a certain path that you've predetermined. And control is essentially getting that vehicle to go on the path that you've predetermined. Of course, there are some error margins, and depending on the design requirements, depending on the mission or the project that you have in hand, those error requirements you will set, and based on that, you will select the type of control you are going to use. There are two types of control: active and passive based control. In passive based control, the system or the vehicle in this case is very inherently stable, and you don't need to expend extra energy into ensuring that the vehicle goes on the path that you have uh, selected. Now, in passive based control, you don't have a lot of control over the system. The system itself, its aerodynamical properties, its physical structure, its inherent math ensures that any deviations from is corrected by itself, and you don't have to expend any energy. You don't have to actuate. You don't have to apply any force to the system to get it to follow the path you want. The other type is active control. In active control, you're actively applying force to the system to ensure that it is following the trajectory you want. And this active control obviously provides much more degrees of freedom. It gives you much more control over the system, and you have many more options of the flight path that you can choose. In passive based control, the system is inherently stable in one or at max two states, and the system will passively be controlled in those states only. So it will go along that passively controlled trajectory itself. You cannot change the trajectory if you want to. In active based control, since you have some amount of force that you can apply, some amount of actuation that you can give to the system, you can provide path correcting forces and ensure that whatever flight plan you want, it need not be the inherently stable flight plan of the system. You can follow that flight plan as well. So, an active control is much more fun, and that's what we're going to be looking at. So, some active control methods. As I said, for active control, what we essentially want to do is we want to be able to apply some external force or talk to the system, and we should be able to change the amount of direction and the amount and direction of the force or torque applied to the system. With that ability to change the amount and direction, that is wherein we will control the system. So in rockets, there are a few techniques common techniques. There are more than these. This is not a comprehensive list here. But one is fin-based control. The fins at the base of the rocket, or you have fins at the top of the rocket, as in SpaceX's rockets, if you've ever seen them. But what these do, they work based on air drag. We control the angle of the fins with respect to the moving air around it. And based on that, that changes the drag that is acting on the vehicle. And since there is a difference in force, that is what we wanted. We have some change in force, and that is what allows us to control the vehicle. Reaction control wheels. Reaction control wheels are heavy wheels which spin up or spin down. So they have a motor catch which we can spin. And these, using the principle of conservation of momentum, provide counter spin. So when these spin in one direction, they'll provide a torque in the other direction to the vehicle it is attached to. So that is how reaction control wheels work. And lastly, but not the least, thrust vector control, what we're here for today. Thrust vector control is as so any system in rockets or aeroplanes needs some amount of thrust to go forward to work. So to control the vehicle, we simply take this thrust and vector it. We change the direction at which the thrust is leaving the vehicle. This is thrust vector control. So as you can see in the image in the right, the flame is slightly away from the nozzle. So essentially, this vector, the thrust has been vectored and is controlling the system. So let's get into a few ways in which we can do thrust vectoring. The firstly and most common one is the gimbaled engine or the gimbal nozzle. So in the gimbaled engine, the engine itself, the entire engine is rotated about the point it is being attached. As in this case, as in this figure here, this is a model rocket. So this works on a solid base motor. And this entire motor inside the casing is rotated. A gimbal nozzle is not rotating the entire engine, but just the nozzle that the flame or the exhaust is coming out of. So since we're changing the direction of the exhaust, again, we have vectored thrust and we have some change in force and change in the direction of the force, and thus we have some torque applied. Now, this depends on what sort of system you have, which one you'll choose. Another one to do thrust vectoring is vernier rockets. These are rockets which are mounted at an angle to the base of the rocket, and these are in a 3 or 4 configuration. So there are either 3 verniers or 4 verniers typically. These, when fired, provide a force vector which does not pass the center of mass or the center of gravity and create a torque. Another case would be using exhaust vanes. So in these control surfaces, or basically fins, some planar surfaces are introduced into the exhaust stream. So they're introduced behind the engine. And in doing so, when we change the angle of these control surfaces, the exhaust leaving the system, the angle of the exhaust leaving the system changes. And in doing so, the reaction force changes and again creates a torque. Here are some visuals of each of the examples that I presented. Credits to NASA. So on the leftmost, we have the movable fins, wherein the fins themselves rotate. And as you can see, the purple line showing the angle at which the force will be applied, like the angle of the fins, and hence the force will go towards the left once we change the angle of the fins. The one to the right of that is the gimbal thrust one, wherein the whole engine has been gimbaled. And so the force is, as you can see from the vector, is not passing to the center of mass. And if you apply simple mechanics, you can see that about the center of mass, you'll have some torque. And the torque will rotate the rocket and give us the control that we need. The third one are vernier rockets. So as you can see, they are small rockets compared to the main rocket, and they are at an angle to the rocket. So they provide force at an angled vector. And again, this angled force will provide torque, which will allow us to control the vehicle. And lastly is the thrust vane. The purple line shows that the control surface has been introduced and it is an angle to the thrust or the exhaust that is coming out of the system. And as you can see, since there is an angle, the force is also angled, and again, it provides a torque. So our main focus will be on the gimbaled engine because in model rocketry and in low power skills, gimbaled engine is the best way to go. It is a rather straightforward technique and it does not require a lot of excess hardware. No other additional rockets, no additional motors, no additional control that needs to be applied for any other of the other systems. So let's take a bit of a deeper look into how the gimbaled engine technique helps us to control our system. So as you can see on the figure on the left, if the thrust has been gimbal towards the left, then our force vector will provide a counterclockwise torque. You can see this by applying the torque, the right hand thumb rule, and see that the torque will be in the counterclockwise direction. If there is no gimbal, the gimbal angle is zero, as shown in the center picture. The force passes through the center of gravity, and we don't have any torque being applied on the system, and that's essentially the zero state of the system. Then on the rightmost case, we have the thrust angling towards the right. So the gimbal angle is towards the right. And that is essentially the opposite of the leftmost picture. We have thrust passing, the thrust providing a clockwise torque. And this small animation shows you how gimbaling the thrust controls the angle of the rocket. Let's tie it all up. So we saw control, we saw gimbaling, and but where does this all tie up to? So how does the gimbal know by what angle should the engine rotate? How does the control essentially work? So all these questions are answered via control systems theory, and this is a subject in itself. In fact, IIT Bombay has a department called Systems and Control, SysCon for short. And in this theory, we study how to go about developing control systems for any system. And this control system theory tells us how much should the gimbal rotate, how much should the force be applied for. And this control system theory is applicable for any system, not just rockets and aeroplanes in general. So let's look at a brief overview of how we would go about it in our system, in our rocket system. First of all, there will be sensors that provide information about the vehicle, about where the vehicle is heading. So basically, the angle of the vehicle, the pitch, the roll, the yaw angles of the vehicle. Then it would also provide information of the velocity and the position. In cases of rockets, position is referring to altitude. We want to know how high the rocket is and in which direction the velocity vector is and how much velocity does the rocket have in each direction. So using this information, there is generally a controller. That controller, it computes the angle that needs to be given to the motor or the angle by which the motor should be rotated. This is determined by, of course, the current state of the motor and the state at which should be. So you'll plan a trajectory for your rocket or your vehicle, and that will have a target state at every point instance. The controller will compare the target state where it wants the system to be versus where the system is and develop an angle or a control signal for the motor. And then further, the control signal is fed into the actuators and which will turn the motor by the required amount. All the above three steps are what the flight computer generally performs in systems like airplanes and rockets. There's a flight computer on board which does all three of these tasks. Now let's talk a bit more about the control law. Control law, and in our cases, it will typically be a PID controller. It takes in the current state and the target state and spits out the control signal. So that's basically a controller or a controller. So here I've given some sources and references for further reading. For information on thrust vectoring, Wikipedia is the way to go, and NASA also has a very good walkthrough on all the topics of rockets, on gimbling and how gimbling works and what thrust vectoring is. If you want to look into control theory, these are two control theory playlists by Brian Douglas. He makes very good control YouTube videos on control theory. The first one is on PID, and the second one is a general control theory overview. And since I love rockets, a bit more about rockets if you want to learn about them. Again, the first one is by NASA, and they have some very good stuff for beginners. And the one is BPS Space. The BPS Space, he makes model rockets, and those model rockets are thrust vector controlled. And so he has many rockets, and he builds them, and he has a pretty open view on how they are built. So you can go through that. That's all from my side. Thank you all. Any doubts are welcome.
Thank you, Nishant. It was a very informative session. Now we are open to questions. If anyone has any doubt, he can unmute or ask.
Hello, Nishant.
Hi, Akshay.
Yeah. So I wanted to ask that in such systems where a particular part of the rocket is completely rotating or completely moving, right? So how do we ensure stability in such a condition? Like stable, even if some parts of it are not not in fully our control or something like that. Stability, basically, I want to ask.
Right. So there's this thing called underactuated and overactuated system. So basically, your system has some degrees of freedom. In rockets, there are generally 6 degrees of freedom, X, Y, Z, and all the three angles, roll, pitch, right. Now, for each of these degrees of freedom, you either want a passive controller or you want an active controller. In a passive controller, say the pitch angle or the pitch angle in a rocket. Generally, you have fins on the rocket, and since it's moving upward, it'll automatically stabilize itself since it's going at a high velocity. So you don't need an active controller. And like roll control, you don't need roll control. In a rocket, you don't really care. In model rockets, at least, you don't control. You don't really care if the rocket spins about its axis. It's
Right.
rolling, and you don't really care about it. So either you don't care about the degree of freedom. You can say that the degree of freedom can do whatever it wants to do. It can go to any state, and you don't care about it. Either that, or you should have some sort of control over it, either passive or active. Only then you will be able to stabilize the degree of freedom and essentially the system.
And for the translational degree of freedom, we will mostly require active controls, right?
Generally, yes, active control is much preferred, but of course, again, depends on what you plan to do.
Okay, thank you.
Welcome.
Anyone else?
Yeah, I would like to ask a question. Am I
do.
audible? Yeah, so
Yes.
like in the 4 figures which you showed, except for the first one, the fin-based one, where there was a center of pressure.
All right.
Yes, that figure. So what is the exact role of this in the movable fin-based control? The others didn't really have that. So, understand.
Oh, okay. About
Hello?
the center. Hi, yes.
Yeah, I wanted to ask other than thrust vectoring, what are the other methods of control?
All right. I'll just first answer Jacob's question and then I'll get back to you.
Okay.
So in this case, what they're doing is in fin-based control, it's based on the air drag of the system. Air drag is something external, while in the other three, we're taking the internal thrust of the system. Agreed?
Yeah.
That's why all forces, as you know, all external forces act on the center of pressure. And that's why they've shown the center of pressure. And the center of pressure is not shown in the other diagrams.
Yeah.
Okay, about other, I don't know, I didn't catch who asked the other question, but other than thrust vector control, so I've listed 2 others. There are many other ways to do it. One is the fin-based control, as this shows. You rotate the fin, so you're not actually vectoring the thrust that you have. You're changing the angle of the fin, and since changing the angle of the fin will change the air drag that is being applied to the system, that will induce a force, and we can use that to control the system. Another is reaction wheels. Reaction wheels are heavy wheels which rotate in the vehicle, and these provide a counter torque to the vehicle. So if you rotate it in one way, the vehicle will rotate in the other, and that will give you some basis of control over the system. Reaction wheels are generally very slow and compared to the other two methods, however. I hope that answers your question. I didn't quite catch who asked it though.
Hi, Nishant.
Hi. May I know who's speaking though? I'd like people to introduce themselves first.
Yeah. Hello, I am Shivam. So, as you mentioned in the control methods, like PID is used as a control mechanism. So, could you
Right.
mention some reference from where, like, we can practice online implementation of PID? Like, we know the theory all, but like how to implement it, like in Python or some other language. So, any other references that you can mention?
So you can go through MATLAB on-ramp. I would suggest that use MATLAB and Simulink to implement PID. You can go through the YouTube channel of this person that I've added. He has some videos on how to make control systems and simulate PID on MATLAB and Simulink. Also, BPS Space has 1 or 2 videos on how to do that as well.
Yeah. I'm asking because like I have a project in embedded system and I would like to implement a PID in that. So actually, that is why I am limited to use the MATLAB.
Oh, okay. So you wanted to. So MATLAB and Simulink, once you develop a MATLAB model in MATLAB or Simulink, then you can translate it to C code. Simulink has this external app called Translating to C code, or in fact, it can directly translate it to something that you can put in an Arduino. So you can check that out. And because creating control systems in Simulink is very easy, and once you do that, you can transfer it out. Simulink does that all for you. You can transfer it out to Arduino code, and you can directly stick it on your Arduino. Of course, you can also analyze the Arduino code and maybe translate it into Python yourself, but that is one route to go. I am not experienced with implementing PID in Python, but I can look up some references and send it through.
Yeah, that will be very helpful. Thanks.
Sure.
Hello.
Hi.
Yeah, so can you open the slide that center of gravity and center of mass? So they are not the same all the time. No? I mean, and for rockets, when propellants burn, the center of mass actually shifts. So when we are designing control systems, do we take it into account?
So I'm talking on a very model scale. Of course, in real rockets, yes, you're right, the center of gravity and center of mass are different, but here we can neglect the gravity variation. They're very small. So center of mass and center of gravity will essentially be same. And again, in model rockets, the amount doesn't really vary all that much. You just have to consider some mass effects. And while designing your PID controller, while simulating, yes, you can check that out. But in a PID based control, you don't really need to worry about that on a model scale, at least. Of course, when we go to real systems like real rockets, then yes, the mass variation is substantial and it is taken into account. And of course, those people don't use PID control. PID control is a very basic controller, and there are advanced controller methods to deal with that.
Thank you.
Hello.
Hello.
Yeah, so I wanted to ask, like, is there some simulation software where we can test our PID, like not working on hardware systems, but only simulation part? So we can like working off our PID on actual model, like we prepare a CAD model and want to implement our PID model on that. So can we do that using some software?
Okay, so the way to test simulations is that using your CAD software, either by some software like the CAD that gives you a model, or by hand analysis, you want to create a mathematical model of the system. By mathematical model, I mean a differential equation that says that if this is my current state and this is my input, then my rate of change of my degree of freedom will be this. So you want some sort of mathematical model which will tell you about the system, that you can solve on pen and paper, that will give you the maths of the system. Once you have that, then you can use Simulink to simulate the PID controller. But in any system, like in any software that I know of, you would need the mathematical model first. And it's fairly easy to obtain a mathematical model. It's not that hard. You can in fact do it by hand.
Yeah, okay.
Yeah, hi Nishant. I am Shivam. I have one more question. So can you I know this question might be a little out of context, but can you tell some aspects about the telemetering from the rockets? Like for example, the inclination data, like how much it is inclined at a time, and what is its altitude and what is velocity. So what kind of particular sensors that we use to telemeter these data to the base station, ground station? Can you present some thoughts on that?
So two things. One would be the sensing part of it. So generally, for model rockets, what I know of, Adafruit and SparkFun provide very good sensors. There are IMUs. IMU is a sensor which gives you information about the tilt of the rocket, the acceleration of the rocket, and so you can do some sensor fusion on that. The other ones are barometers, which tell you about the height of the rocket, and that works on based on the ambient air pressure. And yes, those are the main two sensors that you require. For communication, you can use any. So depending on how far your vehicle is going to go, you can get pre-built communicators in the market. They're generally for stuff like for model RC airplanes. Of course, you can even get pre-built flight computers, entire flight computers, which have the sensors, the control algorithm, and the communication all integrated. And those are also available in market. So depending on the amount of effort that you want to put in and the amount of knowledge you have, you can either go for the entirely pre-built version of a flight computer, or you can try to build one yourself. I hope that answers your question, or did I get it wrong?
Yeah. So by IMU, you means like modules like MPU 6050. These things will work here.
Right.
Like the
BN
basic
nodes.
accelerometer and gyrometer. Yeah.
Yes.
Yeah. Okay.
Okay, so we can take rest of the questions at the end.
So basically, we have launched a series of projects in which you will get an opportunity to join us and work with us on them. Presenting to you the first project, which is the thrust vector landing rocket. I'd like to introduce to you the team members. If you could just say unmute and say hello. Ajay, Amar, and
Yes, hello everyone. I am Amar and I'll also be working on this project, the thrust vector landing rocket.
Hello everyone. I am Ajay and hope to see some of you with us. Thank you.
Yeah, and I'm Swarna. So I'll just give you a rough overview of what we'll be working on in our project. The problem statement that we'll be working on is to make an electric rocket that uses thrust vector control mechanism. The model rocket would be capable of landing autonomously after it has attained a particular height. I hope that it's clear. Next, coming to the learning opportunities, there are no prerequisites as such. We'll be starting from scratch. But yeah, it's of course a plus point if you're already familiar with some of the basic concepts. So we'll be looking at the physics. We'll be looking at the physics behind the thrust vectoring and how it works, how it can be achieved. And we'll be also looking at PID controllers, a bit of control theory for tuning and regulation of our model, and to take in the information about the state of our vehicle. We'll also learn weight iteration and estimation to calculate the amount of thrust which the model will provide, the maximum thrust, and all those stuff. Coming to software and programming languages, and as we all know, due to the online nature of things, we'll focus more on the simulation part, and if possible, we'll try to later implement it in hardware. So for simulation, we'll be using MATLAB, basic MATLAB. MATLAB Simulink for modeling and simulation of a model. And we'll also be using MATLAB 3D Viewer. So that was all from our side. Hope that the project is clear, and we'll be floating a Google form in the chat right now. So if you want to be a part of the project, please do fill out the forms. Thank you.
Thank you, Swarna. Now we can continue with the doubts.
Hello.
Hi.
Yeah. May I know how long is the project like projected for? Like the duration?
The project, the timeline of we have made a timeline. The project is a year long. Well, basically, we'll try to complete it within 6 months. That would be the rough timeline.
Okay. Thank you.
To add to Swarna, basically we'll be starting with online model simulation. Like we'll first do everything online, and then if possible, if the institute reopens, we'll try to implement that in an offline mode, and we'll try to create an actual rocket model which would land autonomously. But until and unless online semester continues, we'll try and keep it in an online manner and do most of the part and do most of the simulations in MATLAB only. So that was the basic timeline.
Okay.
Any more questions about the project or in general about trust vectoring? So I think there are no more questions. It was a wonderful session, Nishant. It was an honor to have you with us. We learned a lot about thrust vectoring, and I think the audience got great knowledge from you. And about the project also, I think many of the audience will be interested. We have already floated the Google form. Thank you so much.
Thanks, Isha. It was fun to be here too. I hope everybody learned something.
Recording stopped. Thank you very much, Nishant, for joining us.
I think we
Yes,
can.
thank you. Yes, thank you, Nishant, for joining, and thanks everyone for attending this.